In this video, we're going to take a look at sequences and establish an overview of the vocabulary and main ideas regarding them. To motivate this discussion, let's consider a ball that is thrown in the air to a height of 50 meters. Now imagine that this ball exists in a place where there's no friction, so that every time it bounces, it's going to rebound to 3/5 its previous height. So a question we might ask is, how high is that ball after its first bounce? How high is it after 2 bounces, 5 bounces, n bounces? We can get a sense of what these bounces will look like by looking at this animation. Each dot on the graph represents a unique bounce height for the ball. Sequences give us a way to examine and answer questions like this one. We're going to use the definition of a sequence given here, which is that a sequence is a function whose domain is the non-negative integers. That means that f of I, where I is an integer, is going to be the ith term of the sequence, which we will often denote as a sub I. That then gives us two ways to define a particular sequence. We can give it an explicit definition where f of n just defines, using a formula, the nth term a sub n, or we can make something called a recurrence relation, in which we define the first term a sub 1, and then every other term is defined as a function of the previous term. In other words, a sub n plus 1 is some function of a sub n. As an example of defining a sequence explicitly, consider the sequence given by f of n equals a sub n is equal to 1 over 2 to the n. We can use that formula to find the first 4 terms of that sequence. We can see that f of 1 would be 1 over 2 to the first power, f of 2 would be 1 over 2 squared, f of 3 is 1 over 2 cubed, and f of 4 is 1 over 2 to the fourth, giving us the sequence 1/2, 1/4, 1/8, 1/16. And using that formula, we can actually find any term that we want at all in the sequence without knowing any of the previous terms. Alternately, we could consider a sequence defined so that the first term is 1/2, and then each successive term is defined in terms of the one before it, so that a sub n is half of a sub n minus 1. Notice then that that gives us the sequence a sub 1, a sub 2, a sub 3, a sub 4 equals 1/2, 1/2 times 1/2, 1/2 times 1/2 times 1/2, and so on, which actually gives us the same sequence we saw in the previous example, just defined in a different way. We'll return to our motivating example, consider our bouncing ball sequence. And for our first task, let's find the first 3 terms of that. We know that the first bounce was 50. The second bounce is then 60% of that, so 50 times 0.6 is 30. And then our third bounce is going to be the second bounce, again times 0.6, so we get 30 times 0.6 or 18. Then let's consider coming up with an explicit formula for the height of the nth bounce. Since the first bounce is 50, and each time we go through our sequence, we multiply by an additional factor of 0.6, it follows that the formula should be f of n is equal to 50 times 0.6 raised to the n minus 1 power, since we don't multiply by 0.6 until we get to the second bounce. Last, let's come up with a recurrence relation to generate our sequence, including our initial value. We know that the first bounce is 50 meters high. We also then know that every time it bounces again, we get 6/10 of or 3/5 of the original bounce. So it's pretty easy to figure out then that the formula is a sub n is going to be 0.6 times a sub n minus 1. Let's get familiar with some vocabulary around sequences. We're going to call a sequence a sub n increasing if a sub n is less than a sub n plus 1. In other words, each term is strictly smaller than the next term. So for example of that, we have the sequence 1, 2, 3, and so on. We'll call a sequence non-decreasing if a sub n is less than or equal to a sub n plus 1. So each term has to be either smaller than the next term or equal to the next term. So if we have a sequence like 1, 1, 2, 2, 3, 3, that is non-decreasing. We can flip those definitions around and define decreasing if a sub n is bigger than a sub n plus 1. And then non-increasing is going to be that each term, a sub n, is bigger than or equal to the following term, a sub n plus 1. If a sequence is either non-increasing or non-decreasing, in other words, it moves in one direction, we're going to call that monotonic. We'll define a sequence as bounded above if we can find a number m so that once our index gets large enough, the entire sequence is less than or equal to m. As an example of that, consider the sequence 1, 0, -1, -2, which is bounded above by the number 1. The flip side of that, a sequence is bounded below if we can find the number n so that a sub n is bigger than or equal to n for all relevant values. There we could consider the sequence 1, 2, 3, and so on, and we can note that that is bounded below by either 1 or 0, or really any number smaller than 1 if we want. Lastly, we're going to define a sequence to be bounded if it is bounded both above and below. So consider the sequence 1/2, 1/3, 1/4, 1/5, and so on and so forth. That's going to be bounded above by 1 and bounded below by 0. To wrap up our overview, we're going to look at some common types of sequences. These are types that we're going to see as we continue through working with sequences and their limits and move on to series. So the first is going to be the arithmetic sequence. These are sequences where the successive terms differ by the same amount. So for example, we have the sequence 2, 5, 8, 11, and so on. And we can see that the difference between every term is 3. We can define that sequence two ways. First, with a formula, noting that the nth term is going to be 3 times n minus 1, and also by a recurrence relation, giving that the first term is a sub 1 is equal to 2, and then the nth term is going to be 3 more than the previous term, so a sub n is going to be a sub n minus 1 plus 3. Another common type of sequence is the alternating sequence. These include a term that forces the sequence to alternate sign, so something like -1 to the n or the cosine of pi times n. And as an example of that, we have this sequence, -1/2, +1/3, -1/4, +1/5, and so on and so forth. Another type we'll work a lot with is the geometric sequence, and these, each term is a multiple of the previous term. So they have the form a times r to the n power, where r is not 0 but is constant. A fairly common example of sequences of this type involve things like compound interest, where we have our principal times 1 plus our interest rate raised to the n power. Our bouncing ball sequence also gives us an example of this type, where in that case our r value was 0.6. We'll wrap things up with some reminders of what we looked at in this video. First, we saw that we can define a sequence as a function with domain in the non-negative integers. We saw two ways to define specific sequences, both using formulas and recurrence relations. We looked at a few examples of each of those. We examined terminology for sequence behavior, like increasing, decreasing, monotonic, bounded, etc. And then we looked at a few common types of sequences.